Right, couple quick sort of announcements type things. Monday, there's no class, right? So anyway, no class Monday. Turns out, no class Wednesday either, since I'm out of town till Thursday night. So, but Wednesday's lecture, I wouldn't want to deprive you of missing a lecture. It's moved to, so I have a Friday lecture in the morning, and then this one will be from 4 to 5 p.m. Now, I realize I'm not expecting you necessarily to show up. It'll be taped, so you can just watch it at home. You're also welcome to the live session, okay, at 4 to 5 in the afternoon. It is before happy hour, so you can't say, like, I got this big weekend. No, you don't. You guys weren't at Fremont the other night on a Thursday. I know you're not doing anything at 4 to 5. Anyway, but you're welcome to come here. But you might have better things. I understand that. So anyway, don't come to class that morning. Don't waste a perfectly good sleeping day to show up here. Okay? Continuing on in that vein, isn't it the next Wednesday, the 27th? I think that's right. 70. Yeah. 20 plus 7 is 27. No lecture that day because I'll be out of town again. So that will be on the Friday, 4 to 5 p.m. So I scheduled the trips Tuesday to Thursday trips, so I don't have to miss one. Note that. Okay. All right, so we're going to start off, continue on with some of the ideas. Last time, we got a bunch of code. We talked about filtering, signal processing through filtering, removing noise. That is one of the main things that people want to do, clean up noise. And it works pretty well if you know what frequency you have to filter and things like this. Now, there are other techniques, however. We've made very little use of things, information so far. If we go back to the example, of radar, this is continually sending out information. We are continually receiving information. Okay? What we did in class is we received one segment of information, one little time slice, and from that little time slice we processed it and found out, hey, there's a little signal sitting in there after I filtered out the noise. Okay? However, you are continually sending out signals and you are continually receiving signals. Right? So it's not like you have just one data set. You've actually got a ton of data. And actually, this is probably many of your problems, is that most of you who are doing your research have lots and lots and lots of data. It's not like I have one set. I have tons of data. I got to process lots of data and see how this thing all stacks up. So what we're going to talk about today is using that information here as well. Okay, so first thing to consider is the following. We're going to add white noise to the system. So in the spectral domain, let's go ahead and take some signal in time. If you Fourier transform this signal, let's go to the Fourier domain. You Fourier transform it. We call this UT, or here we'll call it U hat. And it is a function. If you Fourier transform in time, you get a function of frequencies, okay, essentially. But we call that K, regardless. So the idea is to put white noise on this. These are frequency components. And this has some space frequency distribution, right, for the collection of frequencies that make up some signal. The idea behind white noise is to take every single one of your frequency components, we have a finite number of them, and add to every frequency component randomly distributed variable. Okay? So you just say, okay, plus, and what we normally do is add some noise for every frequency component, let's call it omega j, with some mean and variance. And typically what I'm going to do here is assume that it's normally distributed. Okay? The reason I write this down is we can say, essentially, we can go and look at this signal, and we're going to keep adding a bunch of these signals together, right? I'm going to send information out, get information back, process it. I'm going to do it again, process it. So one thing that you could think about doing is, if I take a whole collection of this data in the frequency domain, I could ask the following question. Here's my new signal, right? It's noise plus signal. I'm going to just write it like this. And now I'm going to take a sum of this stuff, and I'm going to say, what's the expectation value? Right? I can just ask that. Look at the statistics of this thing. I have a lot of data. Look at its average value. And so essentially, it's expectation of this. Now, expectation is an integral, so it's linear. So you can just essentially write this as the expectation of this noise process. If it's a normally distributed Gaussian with mean 0, what is that? 0, exactly. So if you want to essentially remove the noise, just have a lot of data. All the noise is going to sort of, in some sense, when you add it all together, I keep adding all this noise together, it should sort of average itself out to 0. And you have this ability, at least in the radar problem, to just keep sending information out. You won't always have that. It depends a lot on your application. You may have, I have 3 sets of data, and that's it. You don't get, maybe you don't have 1,000, okay? But in a radar application, you can have lots and lots of data, which allows you to just basically eliminate this. And what you're going to get at the end is this sort of average value for the spectral content. Okay? So that's kind of a nice way to process this. You know, there's no filtering. Essentially, it's averaging is filtering in a way, okay, for the white noise. All right, so we're going to spend the whole time working on MATLAB today. You ready for that? Me too. All right, how's everybody feeling today? It's Friday, second week. I know it's a little depressing with all the rain outside, but today we do a little MATLAB in the morning, and it's like coffee for your mind. So a double shot, really nicely made Italian coffee. So let's start with that. Your day can only go downhill after this because, you know, this is your highlight. I know. You don't have to tell me. I know how precious this time is for you. See if this thing is on. Okay. So everybody's good with that? That's a very simple concept. We're going to use it. Okay. So a couple of things, by the way. I put a lot of code in the notes. And the one thing you should see about the notes is that you'll have a lot of practice codes. So for those of you who are warming up to MATLAB or don't know it as well as you think you should, or no matter how much of a pro you think you are at MATLAB, what I find about MATLAB is you always find somebody who maybe you think you're better than they are at MATLAB, and all of a sudden they go, oh, have you tried this command? And you're like, I didn't even know that existed. No matter how experienced you are, you always find somebody who can teach you something about MATLAB. And so these codes are nice starting places to just learn some stuff, kick around. You should know how these codes work because you're going to build codes like this throughout the course. And so we're going to start, you know, building from there. Okay. So here's what we're going to do. We're going to start off with this very basic idea that we have here, which is I wrote the little pre-code to just give you. So we're going to start off with a time slot, 30. It's actually, if you look what I'm going to do here, I'm going to chop this up into a number of Fourier modes. That's going to be my resolution in frequency. And my time is going to be from -L to L. So in other words, I'm going to have a window of time of 60 units chopped up into 512 points. Okay? So that's what this process does here, where remember, the whole reason for having T2 is that you have n+1 points. The last point is the same as the first. It's periodic boundary, so you throw away that point, and here are your actual points, T. Okay? So those T points right there tell you your time domain resolution. Now, the one thing we're going to learn is that from about the mid-'80s, right? 86 rules. Yeah, throw it out there. So from the mid-'80s, before that, basically, the tool you use for signal processing was Fourier transforms. But the mid-'80s, you had this kind of revolution towards what are called wavelets. And we're going to learn about wavelets probably I would say next Wednesday, but since Wednesday is really Friday, so next week on the double lecture day, we'll do a little bit of some wavelets. Because I haven't told you all the shortcomings of Fourier methods yet. We're right now on a very positive note. Everything looks great in our world. Okay? We'll take off the rosy glasses next Friday. For right now, there's your time. Here are your frequency components. Remember, you put it on a 2 pi periodic domain. So you normalize it to the 2 pi periodic domain. You define your Fourier wave numbers right there. So you have cosine 1x, cosine 2x. These are just integers. And remember, the whole reason I wrote it this way is because we know when we Fourier transform, it's going to shift things. Okay? So this k here is pre-shifted. All our manipulations with k have this shifted k here. But when we're going to plot this thing in the frequency domain, we want to plot it in the unshifted domain. And so I've defined ks, which is this k, back to what it should be, which is unshifted. Okay? And noise, that's going to be our noise strength. Start off with 10, which is exactly where we had it yesterday before we filtered. So with a noise strength of 10, at least for what we're doing with this number of Fourier modes and this size domain, when we put noise 10 in there, you couldn't really see a signal in time or frequency. All you saw was junk. Okay? And that's what we wanted to clean up. Okay? Everybody good? Starting point. So let's start defining a signal. And again, I'm using very basic signals, but who cares? This is, we just want to illustrate concepts. Okay? So our signal is such t. Its Fourier transform is ut there, which is just calculated by this. So now we have the signal and its Fourier transform. So let's just plot these so everybody knows exactly what they look like, sort of for the ideal case. So we can plot t versus u, and then we can, on another plot, ks versus fft shift of ut. Okay? So there you have it. Remember, this Fourier domain multiplies every other component by -1. So what we'll do is usually plot the absolute value, and then you FFT shift that. And so this is, there it is. Okay? There's your signal. There's its Fourier transform. Ideal case. So let's just say I had no noise. We just send out stuff, get this back. No interference from anything. Okay? That's the perfect signal we're trying to reproduce. Okay. Same thing as we did yesterday. We're going to add noise to this thing. Okay? Now, we're going to add noise, and we're also going to do one thing, which is, this is one measurement of an experiment. Suppose these are seconds. I took a signal, a sample size of 60 seconds. I process it. I take another signal of 60 seconds, I process it. Take another signal. I can keep taking these things. Okay? So this is just one data point that I have, or one realization that I have of data. Okay? So what we're going to do in this is going to construct a bunch of realizations. Assuming that I can keep drawing in data, let's keep drawing in data. Okay? And then process that, or look at the average of that. Okay. So with that in mind, I'm going to do the following. I'm going to sort of set this up to do this. I'm going to decide, and we're going to do this averaging process, right? So I'm going to decide that I'm going to say, okay, I want to do some realizations. So I'll make a variable called realize. We have one realization, or two, or 5, or 100. Okay? So in other words, that's what I'm going to use to average. I'm going to take one data set, or 2 data sets, or 5. We can play around with the numbers, but this will be very helpful to illustrate what we want to do here. Okay? And what I want to do then is go through, define a variable jj, which is 1 to the length of realize. Actually, let me do this a little more simply, just so you see it more clearly. Let's just do this. I'm not going to make a loop. We'll just plot one at a time. Let's do one realization for the first time. Okay? So I'm going to run this thing 1, 2. So 1 to 1. It's going to go through this once. Right? So if I have a 100 realization, it's going to produce 100 data sets. At 5, it's going to go through a loop 5 times. Each time, put in some new white noise, extract things out. Okay? Okay, so that's my loop for going through the different data samples. Okay? And so what do I want to do in here? Well, the thing I want to do in here is add noise to my signal. So my noisy signal, what I'm going to do with my noise is say, okay, I'm going to take my UT, which is my transformed variable, and add some noise to it. And we did this last time. Rand n, 1 by n, plus I times rand n, 1 by n. There. Okay. What we just did is we just took this Fourier transform, added a bunch of noise to it. We can look at both the signal itself, or the frequency domain of it, and if we inverse Fourier transform that, we can look at the signal itself. Okay? So let's do that. So the signal itself now becomes U of n is equal to, okay, I've added noise, I've inverse Fourier transform it. I can start plotting things directly from here. Okay? So what I'm going to do is the following. Just so we get an idea of what goes on here, let's plot. Subplot. I'm going to plot on the top plot. I'm going to plot the noisy signal, TUN. Oops, subplot 2, 1, 1, plot. Okay? Everybody go with that? And on the bottom plot, I'm going to plot the Fourier transform of that signal, which is just you plot Ks versus FFT shift of the absolute value of UN. Okay? So what I'm going to do is I'm going to go through this thing, and actually, let's just go ahead and do like 3 realizations. What I'm going to do in this thing is I'm going to plot these things. I'm going to say pause 1. It's going to drop for, well, actually do pause. It's going to, 3 seconds is going to show up on the screen for 3 seconds, and then it's going to do the second realization, third realization, so forth. So if we do this, there, oh, 3 seconds is a long time. Okay, so those are just 3 realizations. Did you guys catch all that? We can do more. Watch this. We could do like 20. I'll just give you 1 second each. Okay? So these are just different, let's say, data coming in to my detector. Okay? I keep reading things off, and the white noise keeps changing what this thing looks like. So spectrally, and in the time domain, you see, I mean, you're trying to detect a signal in here. Now, this one is a little bit, you can kind of see there's sort of a consistency of a pulse there. There's something there. You cannot see it at all, right? But part of what we want to do is try to extract things from this. This is what we would read in. How many times did we do that? Is that 20? So what we did is we took 20 measurements right there. And so what we want to do is say the following. If this is really noise, white noise, then if I just kept adding the signal on top of it itself, right, it should start averaging out all this stuff. Because all this stuff here, I know because I've already built the code, all this stuff here is white noise. So if I keep adding it together, its average is 0. So over a lot of realizations, this stuff should just go to 0. Anything that's not white noise will stay. Okay? So let's see if that works. So what I'm going to do now then is say, okay, so I'm going through, I'm doing all these realizations. And we can plot these things over and over again. And then we have a new variable. And here's our new variable. Let's call it UAV for University Avenue. We can get anything you want. Okay. Or it could be U average. That's clearly not. And what we want to do with this is basically take our current average and add to it that noise. Okay? So we better tell it what to start with, by the way. UAV, by the way, is just a bunch of zeros. It's a column vector like this. So we start off with 0. And what you do is every time you get a noisy realization in the frequency domain, here it is. So you have the. So first we're going to work on just the frequency domain for a minute. Okay? So we're going to average over the frequency domain. We're going to take our spectral content, there it is, add it to the previous, add it to the previous, add it to the previous, and just keep adding it. Okay? So UAV is going to have all that information. Now, what we want to do here, let's make a, actually, yeah, we can just keep going here. That's what we did last time. I'm going to plot here. There's the following. Now that we have this average field, we're going to plot is KS versus FFT shift of the absolute value of UAV. Okay? So we're going to keep track of this variable. And in addition to what I plot that, I'm also going to plot on that same plot KS versus UT. Oh, sorry. FFT shift of absolute value UT. In other words, this is the ideal signal. One last thing I better do, by the way, if I keep adding these things, it keeps getting bigger. I want to just normalize it all. Okay, so let's just make it, we normalize it to height 1. Okay, so I want to just divide this by whatever the absolute value of this thing is. Is everybody okay with that? This is just a normalization trick. Yes?
Do you still need the FFT shift when you're plotting just UN?
Which one? Here?
Yeah. Or do you want to plot UTN?
Oh, yes, I do want to plot UTN. Sorry. You couldn't even tell because it was noisy.
Well, you could see kind of going out.
Oh, okay. Yeah, so let's, so that, yeah, thank you. That's UTN. Nice. Gold star for Roe today. Roe, if you want to go outside and hang out in the sunshine, please feel free. All right. Yes, you definitely want UTN, not UN. Okay? Now let's normalize. So I have this all normalized by the max of the absolute value of UAV. Okay? And this is going to be normalized by the max of absolute value of UT. Okay? So just a normalization. So in theory, what should happen is I should have 3 plots. And on the top plot, you're going to see every realization is going to show you what the data is currently, my current measurement in time, current measurement in frequency. And in the bottom plot, what we're going to see is as I start averaging these things together, what I start to produce along with the ideal thing. Okay? So let's do this, and let's actually do something like 50 realizations. Let's see if this works. Okay, there we go. Here we go. 3, 4, 5, 6, 7. Now, you can clearly see, you still get a lot of noise here. Look what's happening to your integrated signal. I keep using data after data after data, and you essentially just denoising this thing. Isn't that awesome? Okay, good. Your reaction says it's awesome. I can totally tell in your eyes. And one second. So you see, just keeps cutting this down further and further and further. As you go to an infinite number of data, this goes to exactly the green line. But look how close it is to the green line, now. And it's what? How many 50 trials or something? How many did I say you go through? 50. Yeah. So it's getting closer and closer and closer. Okay. And there it stopped. So 50 trials, and you've pretty much removed all the noise spectrally. Yeah. So, Kristen, you have?
Yeah. So what would happen if the thing was moving?
Yeah. So we're going to do that next. Come on, don't give it away. Shh. That's like where it says, you go on a web page to read about a movie, and it says, "Spoiler alert." Thanks. As it is right now, let's address this issue. which is you could say, hey, I can do this to the time domain signal as well, right? It's sitting there. I can just keep averaging this, and if I keep doing this, it's just going to pull it out right there. Fine. Very nice. That's assuming the target never moves. Shoot it. Now, that's fine if it's a helicopter, right? I mean, if it's a helicopter hovering, like King 5 News, sitting over downtown traffic. Oh, yeah, it's looking really bad. You can detect it by a bunch of measurements, okay? However, if things moving, then things all over the place. So you start averaging, and it's not going to be there. So we're going to do that next. Okay. But one of the things that's interesting about this, we know, at least in the limit, as you do a lot of trials, it gets cleaned up very nicely. We haven't done any filtering. And yet, here's a clear signature of something. So for instance, in optics, the field I do a lot of work in, when they do a lot of optics experiments, typically stuff happens on very fast timescales. I work in femtosecond, picosecond optics, so stuff happens on a very fast timescale. They often can't resolve the time domain, but what they did is get all the spectral information out, and what it is an average of stuff. So if you see any signatures in the spectrum, it's clear that it's some kind of phenomenon that's generating that, right? So for instance, you may just be using this to say, I'm shining a laser on a sample, and I have lots of data, and I know it's noisy, but what I do is I shine it on there, and I get information, and I get a bunch of spectral peaks. And that's telling me something, right? Right? So the idea is if it's averaged over, all the noise should hopefully disappear, and you get spectral peaks left over, okay? All right, so that's one example there of that. But the other thing I want to show you, and let's go a little more slowly now, and I'm only going to go to 5 realizations, but I'm going to give 4 seconds between. And I'm going to show you how quickly you can almost make an identification of something in there. So when we do this, let me put it here, there's 1 realization. You can't really tell if anything's there. 2, you're already getting a signature that there's something. 3, right? It doesn't take a whole lot of data to take out that noise. There's this big thing we asked about statistics, which is, when I take small sample sizes, can I make accurate predictions about things, right? This is where we get in trouble sometimes with statistics, which is, okay, based on a sample size of 5, I'm trying to make some very general statements about some kind of statistical distribution, okay? And it is dicey, but even here, 3 realizations, clearly there's something there. Or at least it would lead you to believe this. Now, how is this useful, by the way? Suppose you have data and you don't know anything about the system. You just, somehow you have some detection process, you do some stuff, you have several measurements, you pull something like this out. What this would tell you is like, hey, maybe I should put a filter around here and look at the data more carefully through filtering. So for each sample, I could just filter around there and actually see if there's something there or not, right? Maybe you don't know that there's a signal sitting at this spot. But doing this kind of analysis tells you, oh, I should look here, I should look where else is a peak. Okay? So it's going to be part of your homework, by the way. Your super sweet homework. That's not up yet for homework 2, but it should be hopefully by tomorrow. It's going to be awesome. It's going to like detect stuff for me in 3D. So you have to get special goggles for the homework. So, all right. So there you go. So that's a very nice application. And now we're using the statistics and the noise. Now let's go back to Kristen's problem. Let's do this again for the signal. Let's just start filtering the signal and see what we get. Okay? So in this application, we can start doing that. We can say instead, let's go ahead, and in this third plot, let's not plot what we did. Let's comment this out. Text, comment. And let's put in something new here, which is subplot 3, 1, 3. And we're going to plot. Here what we want to plot is the ideal signal. Well, actually, let's go ahead and plot the average. So now let's do, instead of this average being of the transform, let's do the average of the noisy field itself. Okay? You take out that t. And so now you just have, I have the noise field. I keep averaging over it. So then I can plot t versus u average, and then t versus u, which is the ideal signal to begin with. And I'm going to plot the absolute value, by the way, because we'll have some imaginary components due to the noise. So let's just plot the absolute value of both. And let's again do pause 1, 50 realizations. There you go. So here you go. Did I not normalize it right? I didn't normalize it. So hold on. I'm just keep adding these things together, right? So you see it getting bigger. So I got to divide that by the total number of realizations, essentially. So Control C. Okay, there you go. Okay, so I want to normalize this by the max of the absolute value of UF. There you go. So here's your signal processing. So for a stationary target, without any filtering, just reading things off, does a great job picking this out, right? So, so for instance, if you are using something like this in signal detection to actually measure things like, for instance, what I want to do is topography of the ocean bottom by sending out some waves and having them come back, right? The ocean bottom, in theory, is not moving on you, right? So you can keep sending data out, but underneath there's big whales that you're blowing up. Underneath there's also currents. The currents that flow under there have to do with the salinity index that comes through the salt, which changes the index of refraction, which changes the sonar, changes everything. So every time you do a measurement, you have noise in there. But if it's a stationary target, you just keep pulling in data, you basically just keep piling on top of each other, and out pulls your signal. All the noise disappears. There it is. Okay? So that's a nice, simple idea using now our statistical probability way of thinking. So we had the filtering ideas that we talked about last time. We have now just using the concept of our probability theory, statistics, and cleaning things up. Okay? So now here's the other question that was asked. What happens if in the time domain this thing's moving around? Okay? Because that's actually what you want to do. If you're going to do target detection with sonar, in theory the thing's moving around like Mach 1 or 2, right? I mean, it's fast. It's not slow. Okay, so let's talk about then building an algorithm or trying to understand that. Okay? So we can come back to this, and the thing that we can do here now is let me come down here. I'm going to grab some pre-code that I built, and so we can be on the same page. It's going to be a really more effective way to program this. Okay. I'm going to break here where we had that previous code. Okay. So here's what I'm going to do with this. Oops. Take this out. Let me just explain this piece of code right here. So we start off with the same stuff we had before. And I'm going to give it some time slices, some data slices, some realizations. 0 to 0.5 to 10, whatever those units happen to be in. I say, okay, I'm reading off stuff, every half hour. It could be every half hour. 0, half hour, hour, whatever. Or it could be every half minute or something like this. Anyway, I have data that I'm collecting periodically. Okay? So I have 21 things of data total here. And what I'm going to do with this is I still have my time domain. I'm going to make up a function that I want to just say the ideal behavior of the system. So I'm going to use what's called the mesh grid command. And the mesh grid command is saying, look, I have my time domain, and I have a bunch of slices of it. So I'm going to make this grid by using what's called the mesh grid command, where time goes this way, and the slice goes this way. Okay? These are just vectors. So you're giving them the sense of direction, x and y coordinates, as it were. Okay? So the mesh grid command does that for you. So you put in your time and your slices, called TS. So now capital T is your time in this coordinate system that knows that it's in the x direction, and S are the slices. So this is like your x and y coordinate system, as it were. And I make something like that corresponding also to the frequency domain. Take my frequency domain, slice it up, and I get this. Here's what I'm going to do. I'm going to take a little Setch pulse again, but as I move it through the different S values, and other y coordinates, its position shifts. Okay? And I'm going to plot it here. So this is all this is going to do. It's going to be just this little pulse that's going to just be weaving like this. Okay? I just made a very simple sine behavior. So when I do this, there it is. Okay? So suppose that's my target, and it's doing maneuvers, right? Okay? Back and forth. Very simple idea. And by the way, all the other little things in the code are just to make things pretty, right? Make the fonts a little bit bigger, make the angle right, put some labels on. Okay. Everybody good with that? That's what I'm going to try to detect. Okay? But now what I need to do is, what does this look like in the Fourier domain? We have to understand that. So I'm going to Fourier transform every single slice of data here. So remember, this is 1 measurement, 2 measurements, 3 measurements, 4 measurements. That's what they represent here. Okay? So in some sense, if we put the measurements together, we'd say, oh, in an ideal frame, what this is something, some target moving around. Okay? So, but I'm going to take this thing, I'm going to Fourier transform and look at what this thing does. Now here's the thing. In the Fourier domain, this is a target. You're still sending out omega naught, bringing back omega naught. It doesn't matter what this thing is doing. I'm still centered around whatever my omega naught I sent out. So even though this thing moves around in the time domain, in the frequency domain, it's fixed. I've given frequency, whatever I sent out. Okay, so let's plot that in the ideal case. All right, so we come here. What do we got to do then? Well, what we've got to do now is make a loop for j equals 1 to the length of how many realizations I have, or slices. So it's going to go through 21 times. And every time I go through this, what I got to do is I've got to say, okay, look, what I want is a transform of that. So ut is going to be, the first column of it, or first row, is going to be FFT, the first row of that. Okay? I pull out a row, I Fourier transform it. I now have it in the transform domain. Okay? And what this procedure here just does, and let's make what's called UTP, which is for plotting purposes only. This is going to be just this thing, and we're going to sort of make it, it's going to work for us. It's just the FFT shift of UT. Okay? So I want to plot UTP. This can be a little easier. And by the way, if it's for plotting purposes, probably what I should do is shift it. I should normalize it and maybe plot the absolute value, actually. So absolute value of this thing and divided by the max of absolute value of UTJ. Okay, so there you go. That is the Fourier transform of this thing. And let's go ahead and make another waterfall plot of this thing. And the waterfall plot of this thing, well, the other thing we need is, right here we have the, let's go send in KS instead. KS is the FFT shifted frequencies, because when I want to plot this, it's going to be K versus this versus UTP. Okay? So I'm going to plot the frequencies versus the slices versus the Fourier transform of this thing, normalized, absolute valued, everything. Okay? So that signal will have the following look. Oops. Unbalanced parentheses. Line 52. What? Or did I copy and paste something that... Did it say line 52? Line 22. Oh, okay. Column 52. All right, so... That's what happens. You misread things. There's one, there's two. Oh, okay, so I'm probably missing one here. Yeah, right there. All right. All right, see. Line 37. I don't want to go to line 10. Didn't I put a break statement here? Let's put that break date right there. Oh, shoot. Okay, that's subplot. Last piece, subplot 212. Okay, there we go. There you go. Okay, ideal behavior. Thing moving around. Look at its Fourier spectrum. Nice, consistent. You know exactly what to pick out. Now, here's the deal. I'm going to just throw massive amounts of noise on this again. Okay, you throw all this noise on. What happens? This just becomes a blur. This becomes a blur. But here's the thing. When I average over a lot of data here, what do? I just clean it right up. When I average over this, this thing is moving all around. So when you average, you get nothing basically out of this thing. So let's go through the same process. Let's do some realizations. As I run the realizations for this time behavior and this corresponding frequency, and I put all this noise on it, we can just ask, if I average over this and I average over that, what happens, right? That's what we want to do. So let's throw some noise on this thing. All right, so right away what we can do is just define what we call UN, which is U. Sorry, actually, we want to throw some noise on this thing. Right, so there's UT. Our noisy transform, what is it? Well, it's just UT plus, what do? We add noise times rand n 1 by n plus I times rand n 1 by n. There's my noise, just like before. So I've added noise to this thing. That's the noisy signal. If I want back my, so that's a noisy transform. If I want back my noisy signal, I say U of n J is equal to the inverse Fourier transform of UT. Okay? So there is my noisy signal in the Fourier domain. Here it is in the time domain. Okay? So that's actually what I want to plot. So let's move this. All this pretty stuff we'll take away. Let's just move this waterfall, or actually this whole thing here. We'll put it here. Okay, so what I want to plot now is not U, but U of n, and not really U of n, but the absolute value of U of n. Okay, there's my noisy signal. Yep.
On the I, D, J.
Oh, yeah. Thank you. Column by column, boom. There's U of n. There's UTP. By the way, now what we don't want UTP. What we really want is we want to throw the noisy signal in there. It's called UTN divided by UTN. Okay, so now in theory, if we did it right, there. The idea is that this is what you get. This is what you detect. Okay, well, there's my signal. There's my frequency. Well, it kind of does this on the projector, huh? Point at infinities right over. Okay, but okay, so that's the idea. The idea is that that's what you would actually get out of measurements when you throw this noise on. Can anybody see? What can you see? We could do Roche tests. Anyone want to volunteer what they see? No? A little too personal? Okay. Well, let's analyze the data and do the kind of things we want to do here, which is one option we had right away is to just filter this. This is what we learned last time. But again, here's the point. A lot of the data analysis we want to start talking about is the fact that I read this stuff off somewhere from some experiment I did. I don't even know where I should look. It's a new experiment. I don't know if there's what stuff is going on. I have no idea about the experiment except that I'm looking at new data and I'm trying to figure out what's going on. So at the beginning of this process, you are not knowing where to filter. Okay? So what we're going to do is just say, okay, the concept here, if there's stuff that has a certain frequency or if there's some physics that it has a signature component here, if we average over this, realizations, remember, here's one realization, here's a second. These are all data slices in time. So we should be able to average over all of this and see if there's some kind of signature there. Okay? So let's do that. All that data is collected in this matrix here, UTN. UTN has all our data. Okay? So if I have all my data in UTN, all I got to do is take each slice of this thing and kind of average it together. So let's make, again, an average vector. Start with UAV equals zeros, 1 to n. And then what I'm going to do is say, okay, every time I make one of these, I'll say UAV is equal to what it was before plus UTNJ. So I added it. Okay? Now I add it there, and I just let it keep adding. I go through all these. I go through each data slice. I add it together. Let's do now 3. Oh, actually, we could probably make a whole new graph, right? We can afford it. And when I have all this average stuff, this is the average field. After I'm all done with this, what I want to do is say, okay, now let's go ahead and plot it and say plot KS versus, what is the average field there? The average field that I get out of that thing is I would want to inverse Fourier transform it, right? So, I want to plot in the frequency domain. So I want to first FFT shift it, the absolute value of UAV. And I want to divide it by normalization. So max of absolute value UAV. So far, so good. I'm just going to plot that. And also what I want to plot in here is KS versus our ideal Fourier transform, which was, let's go to our ideal Fourier transform, which was FFT shift of UT. This was without noise. This is the Fourier transform of just the signal without noise. And let's do the first row of that, divided by the absolute value, the max of the absolute value of UT1. Okay, and actually we want the absolute value here too. So what I'm going to compare it to is the noiseless signal. Let's see if I did that right. No, I knew it didn't. Okay, we're missing something. Yeah, okay, fine. All right. Who was counting my parentheses? Nobody? This is how you can stay awake in class. Some people count sheep to fall asleep. You could count parentheses to stay awake. Where there? Okay, not there, right? Maybe somewhere over here. Is it over here, all the way at the end? Yeah. Let's try that. When in doubt, add a parentheses. Did it go? Oh, still there. Okay, that's not where it was. All right. Okay, that one. Oh, that one's for that one. Oh, we still need one more then. Yeah, there it goes. See? Oh, look at that little handy deal. Okay. Okay, figure 1 and figure 2. Whew. All right. There is the sort of the end result. Look at that with about a minute to go. But here, this is it. So you took these slices of data. By the way, if I were to average the time domain, I would just get a mess. I'd smear out my signal completely. I have 21 slices of data, and I ask, is there anything there? And all I do is average over the data. I get a clear signature of something. So it tells me, oh, look, there's some kind of thing there. I should investigate further here. Maybe I put the filter here now and start doing filtering. Okay? So this is yet another way to think about doing data analysis. Now, the one thing I didn't talk about is this. Fourier transforms are used heavily to do this kind of stuff. But one of the problems with the Fourier transform is the following. Suppose I want to get really good resolution of this thing. What ends up happening in Fourier transforms, very good resolution in time, means really bad resolution in frequency. Really good resolution in frequency means very bad resolution in time. The fact with the Fourier transform is you have these competing effects. And what you ultimately want is excellent resolution in time and excellent resolution in space. Okay? You want to capture all of it. You want it all. You can't have it all with the Fourier transform. Okay? So we'll move on to other techniques next time. Have a great weekend. You can turn in your homework now or email it to me, whatever. Okay.